It's now time for us to move beyond sentential logic and into the domain of what happened in the 20th century in logic. So this new logic, 20th century logic, is called first-order logic, sometimes called the predicate calculus or quantification theory. The core innovation that distinguishes modern logic from its predecessors is its concern with parts of sentences rather than with the whole declarative sentence. So especially important in modern logic is attention to what are called the quantifiers. So the quantifiers are words that indicate something about the level of generality involved in the claims the sentences are making. So the basic quantifiers that serve as the focus for our study in this part of the course are some and all, these two words. But words like none, everyone, everywhere, nowhere, and many other terms in ordinary language also behave in ways that involve quantification. Now, traditional logic didn't shed any real insight into the logical behavior of these concepts. And while Aristotelian logicians discovered reasoning involving all and some, their logic was very limited in what it could capture, what it could formalize, especially when compared to modern first-order logic. So in this part of the course, we introduced the necessary techniques for strengthening the expressive power of our formal reasoning. And with this additional expressive power, we get lots more insight into how we can reason about generality. So given sentential logic alone, we quickly encounter limits to our ability to capture some of the logical relationships and valid reasoning that we can easily express in ordinary language. So the declarative sentence by itself is too clunky or too coarse-grained for the kind of analysis we need to do to capture our reasoning about some and all. So in this part of the course, we'll show how to unpack the parts of a sentence in order to find the kind of logical structure that sentential logic conceals, really hides. So remember that in sentential logic, a declarative sentence like all frogs are amphibians would be represented using a single uppercase letter, say a capital F. And as we've seen in sentential logic, we can study the logical behavior of structures that result from connecting declarative sentences using operators. So all frogs are amphibians, F, or the cat ate breakfast, C, joining the two with the or. So these could be represented as two declarative sentences joined by that logical operator or. So we'd have F, the symbol for or, the wedge, C, F or C. Since sentential logic deals with arguments on that scale, on the scale of declarative sentences, its resolution is limited. As we'll soon see, there are a number of important features of arguments that sentential logic can't catch. So the next step then into the world of first-order logic involves unpacking the declarative sentence in order to reveal additional inner structure, the inner logical structure of the sentence. So as we begin to uncover the inner structure of the declarative sentence, we'll find that sentences have distinct kinds of parts, and that these parts interact in ways that underlie some important patterns of valid reasoning. So specifically, the additional parts we'll look at, the quantifiers, predicates, and names, add to the structure that logical operators provide. So a sentence like all frogs are amphibians has parts that contribute to the kind of judgments it allows us to make, the kind of inferences it allows us to make. So before we can focus on the parts of the declarative sentence, it's worth considering what kind of logical structure sentential logic misses. We'll say a lot more about this later. So if I know that Wolfgang is a frog, for example, and if I know that all frogs are amphibians, then I can validly conclude that Wolfgang is an amphibian. And notice that the word all is playing a crucial role in that inference. So to begin with, if we're restricted to representing declarative sentences as unanalyzed units, we miss the kind of logical structure that would allow us to understand why a large class of similar inferences or arguments are valid. So another example of the kind of logical structure that we have in mind here would support the following valid inference. So let's say I know that Marie bought a car, and let's call this sentence M. From M, I can legitimately conclude that someone bought a car. And notice that this someone bought a car is a different declarative sentence. Let's call it C. So the inference contains, moving from M to C features the logical operators that we've become acquainted with so far. But M and C are distinct. So how can I be guaranteed that this is a legitimate piece of reasoning and not a simple non sequitur? What I mean is sentential logic alone won't allow us to represent the inference from M to C without any additional explanation or analysis. So by the end of this part of the course, you'll, I hope, be able to detect the inner structure that allows for this kind of inference. And you'll also be able to formalize that structure in the language of first-order logic. And from there, we'll learn how to generate proofs that show the validity of arguments that depend on these structures. Okay, thanks.